Welcome to the Chem Doctor, and I am proud to say this is the first video in the series that's going to start to deal with organic chemistry. And what we're going to do in this presentation is start the process to learn how to draw basically the condensed formulas, chemical formulas for organic compounds, and learn how to translate those formulas into line drawings. Now, any student who finds himself in a sophomore level university organic chemistry course, you need to go back and review your Lewis structure or your structural drawing capabilities. You need to practice your Lewis formulas and make sure that you can calculate formal charges, that you understand the relationship between electronegativity and being able to identify polarity of molecules and so forth. You can find a whole bunch of videos at my website, www.chemdoctor.org, under the link Lewis formulas. So let's go ahead and begin, and this video is going to be, we're going to keep things simple and focus on one molecule. So if we look at the molecule called butane, and this is from the alkanes, all right? And the alkanes, perhaps on one level, are the simplest collection of organic molecules. These guys are what we call the hydrocarbons. Hydrocarbons because they're composed of only carbon and hydrogen. You should make sure that you know the first 10 of these by heart. They start with methane. All right, and then they build one carbon unit at a time. So the next one here would be ethane. All right, and then we're going to have propane. Oops. Then we're going to have propane, which has actually 3 carbons in it and 8 hydrogens. All right, these are all single chain, what we call single chain hydrocarbons. So this is butane here, which is actually our next one. And you can see that they're growing by literally 2 hydrogens at a time. 1 carbon unit and 2 hydrogens at a time. The next one after this is going to be pentane. And then we're going to have hexane. So this guy is pentane, this guy hexane. All right, and then C7, H16 is going to be heptane. And then C8, H18 is octane. And then C9, H20, nonane. And then finally C10, H22, decane. So these are the first 10 alkanes. They're all what we call straight chain hydrocarbons. What do we mean by that exactly? So if we come up here to my model compound, butane, we can extend the structure of this. All right, and what we're going to do next is draw what's called the condensed formula. So the condensed formula is going to imply ownership of the hydrogens onto a specific carbon. So the condensed formula of butane is going to look like this. All right, if I draw the extended chemical formula of this now, the Lewis dot, I guess some would call it the Lewis dot formula, only we're not going to show the electrons as dots, we're using dashes. Then the extended formula or structural diagram will look like this, where we actually show the bonds to each of the carbons. All right, and you see that for the internal carbons there are 2 hydrogens each, and then we've got on the external, the 2 carbons that are on the ends, there are 3. Note that in every single case, the carbon has got 4 bonds around it, a total of 8 electrons. And this is something that we're going to always see in common in any of these diagrams, your carbon is always going to have a total of 4 bonds to it. Even when we look at double and triple bonds, if you count the number of electrons, there's always going to be 8 electrons around the carbon, except in situations where the carbon is ionized. But for now, we're going to keep things on a more simple level. Now, what I want to do is draw what's called the line drawing here. And the line drawing is a way that organic chemists write structural diagrams that allows us a shorthand method to represent this molecule that's easier to draw. The key thing is that by convention, we're going to be leaving out the hydrogens. Remember that for single bonded carbons like this that have a total of 8 electrons around them, that the hybridization here is sp3. And so the alkanes, or the hydrocarbons, are all sp3 hybridized carbons. They're all tetrahedral. And the bond angles around every carbon are 109.5. All right, now why am I bringing this up? Because we're going to draw a line drawing here, and what we're going to do is just represent basically the carbons, and we're going to use a zigzag pattern to do that. So for butane, the actual line drawing is going to look like that. Now, how do you interpret this? At each end, there's a carbon, and in each place where there's a bend or a change in direction, there's a carbon. So I'm going to go ahead and label those. So we have a carbon here, a carbon here. Let's see, I'm going to give these numbers too. So C1, C2. We have a carbon here, and we have our 4th carbon here. And notice that we've left off the hydrogens, so by convention they're not shown here. It would be incorrect to write the structure this way. All right, this way is not acceptable. If you put the C's in, then you also have to put the hydrogens in. You don't have a choice here. So if you're going to use the carbons, then you've got to go around and put the hydrogens back in. So we would do this to make the structure correct. Now, you can argue that the bonds here, or that the bends, more accurately represent the change in bond angle as we stream through this molecule, because you need to remember that this is being a single bonded carbon and sp3, that all of the bonds here are 109.5. So that's reflected in the zigzag structure here. Although you can't take this in an absolute sense, because we're going to use the line drawing to represent a lot of different molecules. All right, and I'll give you a couple examples of that right now, and then we're going to close the video to keep things simple and break this out into steps. So very quickly, let's look at a different kind of molecule, like perhaps acetone. All right, and acetone has this structure that you hopefully have seen before in your general chem classes. We can draw the if we want to draw the extended structure of this, then we would represent each terminal carbon this way. Bring our hydrogens out. All right, and then I'm going to redraw that carbonyl carbon. Carbonyl meaning a carbon that is double bonded to an oxygen. And then we're going to have the extended structure here off of this carbon. So we're going to show all 3 hydrogens. Now the line drawing is going to look like this. Notice a couple of things again. First off, we use a stagger, or a bended conformation, if you will, so that we can see where the carbons are. All right, so we have 1 carbon here. We have our 2nd carbon there, and the 3rd one here. All right, notice on the oxygen we left off the 2 unshared pairs of electrons. And I'm going to be talking about how we interpret that. All right, so those are left off by convention. How do we know that there's two unshared pairs of electrons there? And that's going to have to do with our knowledge of formal charge. Notice that there's no formal charge on this oxygen. And with a little bit of practice, you'll be able to understand that that will always be an oxygen with a lack of formal charge that's going to have two unshared pairs of electrons on it, and essentially the same conformation of water. But we'll come back and we'll look at that later in subsequent videos. All right, so this diagram right here and this one, this guy being the one that's hardest to draw, for example, or similarly this diagram, which is hardest to draw because you basically have to show the existence of every single bond in the molecule, are vastly simplified when we go to a line drawing. All right, this is considerably easier to draw than either of these other diagrams that I have here. If we look at one final example, all right, let's take a look at this molecule. This is actually an alcohol. It's called an alcohol because of the presence of this OH group here on the end, which in organic chemistry we call a hydroxyl functional group. All right, and a hydroxyl, in another way of thinking about it, is literally just part of a water molecule. All right, if you view a water molecule like this for a minute, and if we were to come in here, for example, and ditch this hydrogen, now you see what we have is what we have actually tacked on to the end of this, what is an alkane, right? Because this is actually a 3-carbon hydrocarbon, right? 3-carbon hydrocarbon, it's an alkane, it came from propane. So we would call this molecule actually N-propanol. N-propanol. So now if I draw the extended Lewis structure for this, it's going to look like this. All right, we put in all the bonds to the carbons, and then we're going to have our hydroxyl or our OH group right here like that. Now, this was easy enough to draw. It's a relatively small molecule, but we can also represent this using the line drawing, and the line drawing is going to look like this. Whoops, I want this cleaner. So the line drawing is going to look like this. All right, and this I'm going to label as carbon 1. This is carbon 2. And here's my carbon 3. And then of course we have our hydroxyl. Note again, and I guess I did it here, that I am leaving the unshared pairs of electrons on the oxygen off. All right, now that doesn't mean I haven't abandoned those electrons, but we're using a notation here that we're utilizing because we want to be able to draw these structures more efficiently, and we're communicating to another chemist who understands that the unshareds haven't been abandoned here. We understand that they're actually present, but because we understand that when an oxygen has a formal charge of 0, then there has to be also two unshared pairs of electrons on that particular atom. All right. So with that, I'm going to go ahead and close this video. I would like to thank the viewer for watching ChemDoctor, and you can find more videos at www.chemdoctor.org.